So I hope I'm audible. So this is the second TA class for the course Game Theory, Strategy and Introduction to Game Theory. And we'll start in a few minutes. I'll just wait for some more people to join in case they're joining. So in the meantime, if you have any questions you would like to ask from week one, you can just post it in the group chat. I will take it up in the class. So I think you have time until first week of August to um, submit your first assignment. So I think you have not missed anything as such. You'll just need to kind of go through all the content of week one. You have not done so already. So I hope you are not getting an echo or anything. Are you getting an echo? Is the sound okay for you guys? If there's no echo, it should be fine. So it's almost time. For those of you who just joined, in case you have any questions or any doubts you want cleared, please can either unmute yourself and speak, or you can just post it in the group chat. Either is okay. So I will also go through first, since this is like the first class. So I will just go over what we will normally be doing in our class from 6 to 8 p.m. every day. And what I'll do is generally I will first take up all your questions to see in case if you have any questions, either from the previous week's assignment or from the coursework or any other conceptual doubts you have. So I understand what all you guys need more help with. And then I will proceed to give a brief recap of whatever is covered in that course through examples. So because this is game theory, there isn't really much theory on its own. Like, everything you're studying through the whole structure or format of games itself. So there isn't like any separate theory in game theory. So we will take up a lot of examples, and I will discuss some examples to first recap the concepts, and then we will take up some more examples to kind of see if you have understood the concepts or not. So we'll take a short break after 1 hour because it is a 2-hour class, and I think some people generally need a little bit of a break. And most of the questions I will discuss will be from different books, or they may not be from any book at all. They may be questions which I have made up or which I have just created to illustrate a point. And some of the questions will be from the previous week. So just so you guys know, you have an assignment every week which you need to submit before a certain given deadline. So every week the assignment has a deadline, and that deadline is visible to you on that, the quiz page. So I hope you guys have seen that. So every week there's a weekly deadline for submission of assignments. So the current assignment for which the deadline is not over yet, I am not allowed to discuss questions from that for obvious reasons. But I will discuss any other doubts or difficulties you might be having from that particular week. Once the submission date of an assignment is over, I can discuss it in the next week. Any problems you have with the solutions of the questions or anything like that. So, is there a message? Right, so since we are almost, it's time, I think it's 6. So I will start. So my name is Aarti Agarwal. I'm a PhD scholar at IIT Kanpur, and I will be one of your TAs for this particular course. And game theory is actually a very interesting subject. My own research is partially in that field, not entirely, but partially in that field. And let's make sure this class is not boring for anybody. That is going to be at least my effort. And if there is anything special throughout the course which you feel you're having difficulty with, whether it is mathematical notation or it is a certain category of games, or it's a certain category of questions, or some mathematical concept which you may not be familiar with, you can let me know about all those things. And we can use this time in the class to discuss those things, because this is ideally supposed to be a tutorial class. So, if you guys tell me what you're actually struggling with, it will be a lot more useful for you. So, okay, so let me start with today's material. Let me just share my screen. Just give me a moment. So today is the first class, so there may be a little bit of teething trouble, but hopefully nothing particularly difficult. So for me to be able to share my screen from a separate device, I have had to enable the feature for everybody, but please don't start sharing your screen. It will make it a bit difficult to do the class. So I hope you can see my screen. Is my screen visible to everybody? Oops. You can just type yes or no. Yes, okay, great. So I will just start in a minute, but before that, I just wanted to know the background of everybody. How many of you are studying game theory for the first time? Like you've never studied game theory before at all? Anybody like that in the class?
Yes, ma'am. I have never studied game theory earlier. So this is my first encounter with game theory. I was kind of fascinated with the word game theory. So I just thought, let's give it a chance. So I'm
wonderful
research. So I think it can help me. Some kind of modeling in my research. I'm basically from the computer science background.
Okay, wonderful. Welcome to game theory. Anybody else who's studying game theory for the first time? Okay, so I'm going to assume others have some experience or some idea of game theory maybe you've sort of familiar with it. Okay. Great. So, I have to start with like the flow of the course because that is the structure, that is the framework of this particular class. Like we are supposed to be doing this as a teaching requirement as a part of PMRF. And so we are supposed to do TA based on, okay, I think my screen went off. Yeah, so we are supposed to do TA based on whatever is the curriculum for that particular course. So I'm just trying to see why my screen is acting up. Yeah, okay, so there's a lag. Should see my screen now. Yeah. So that is why I can't take too much which is out of scope for this course. But whatever is within the course framework, even if it is pertaining to say your other subjects, research, whatever, we can still discuss that. So first of all, I will talk about what you can use as reference reading. So this particular slide is going to be there in all my slides. And also these slides, this PPT slides, which I'm sharing in the class, I will share it in the shared folder. It is a Google Drive folder, which is visible to all. And I posted the link for this meeting link and the Google folder, everything on Google discussion forum. In case you have not seen it till now, you can just check the Google discussion forum where I've shared all of this. And after the class, I will upload this PowerPoint thing. Yes, the recording will also be available on YouTube and the link will be shared with you by NPTEL in case there is a lag, because sometimes NPTEL is a bit overloaded, so they may take a little bit of time to update the links and all that. So I will share the YouTube playlist link also on the Google discussion forum. So, it's easy for you to find. Sometimes people are not able to find the links. I've seen this in every class. This is, I think, the fourth NPTEL course I'm teaching. So I'm kind of familiar with the issues people face. So just so everything will be shared with you. That said, if you want to try out the examples which I will be discussing in the class, I'd encourage you to sit with a pen or paper or pencil or something where you can write out the things yourself. That will immensely help you. Okay, so for reference reading, these are the 4 books which I would recommend and which I myself have used. There are many books which you can refer to for advanced material or for specialized areas of game theory, because game theory has applications in so many fields, right? So these are still the books which I think are at the level of this particular course, and which all these 4 books kind of complement each other. So Games of Strategy by Avinash Dikshit and Susan Steith is it's a pretty good book, and it's a nice book to read if you really want to read a lot. They've given a lot of very interesting games from TV shows, from movies, from historic happenings and all that. So, if you like that kind of stuff, you can refer to Games of Strategy. The second one is Introduction to Game Theory by Martin Osborne. And this is also a good book. In this, he has covered a lot of classical games. And the treatment is slightly different from Dikshit. So you would benefit from this also if you want to just be very rigorous with the classical games. His material, his treatment is slightly rigorous. And the third one is Joel Watson with the same name as the course. And this one is also, I find it a really good book, but the arrangement of the course material is very, very different in Watson. So he starts with extensive forms games, then he talks about rationalizability, then he talks about, the Nash equilibrium, all that. So his arrangement is very different for the game. So you may initially, want to put Joel Watson on hold, or if you want to read Joel Watson, start with the chapter on best response in Nash equilibrium, because he starts with a chapter which we haven't covered yet and which we won't cover for another 1 or 2 weeks. So don't get confused. Everything we're discussing is there in the book, but don't start with the first chapter. And the last is Strategies and Games by Prajit Datta. This one is, again, a very good book and slightly rigorous. He's given a lot of examples, some worked out examples, some not worked out. So some of the very popular games you'll find in all the 4 books, but some of the books have some extra kind of variations of the games or some slightly different treatment. So for mathematical stuff, I would recommend the 4th book, the book. So that one has I find the mathematical treatment in the last book the best. That's just my opinion. I mean, you can check it out, but that's going through a whole lot of books. I find this one to be the most intuitive and the easiest to understand mathematically. This is for your reference reading. Of course, apart from this, there are many other books. You can refer to most of the book. If you're from economics background, you can refer to the usual Halvarian, MWG. All these books also have, separate dedicated chapters on game theory. So if you want, you can refer to those. But these are the books purely on game theory, which I think would be good for everybody. So just to recap, whatever is there in week 1. Where's the times? This is being recorded, right? I'm just checking if it is being recorded. I don't know why it's showing only 5 minutes recording. It should be showing from the beginning.
Yes, it's being recorded. There is a timer which is on.
Yeah, but it's showing only 6 minutes recording, but it should have been recording for 12 minutes. That's what I'm
on my screen. It's
worried.
showing 11 minutes.
It's showing, sorry, what?
11 minutes.
Okay, then it should be fine. I mean, it doesn't make a huge difference, but it just, I don't want it to clip the initial part. If it's recording, then I think it should be fine. So coming to a strategic game. So there is the word game is used very loosely in the English language, even in other languages for that matter. So it is a bit important to understand that within the ambit or within the purview of this course, what are we really, using the word game or strategic game for? What do we mean? So when we use the word strategic game or even just game in this particular course, we are automatically implying a few things, right? And those things, whether it be like a really complex game or a really simple game, in the entire length of this course, these few things are going to be assumed as understood or implied in this entire set of problems we will discuss in game theory. So first of all is that in this particular game, we're not talking about, say, like in English language, you usually say sometimes the game's nature play or whatever, or the game's does God roll dice, blah, blah, blah. We're not talking about those things. We're talking about very clear players and agents. It's clear who is a player or who is an agent in this game. There is no doubt about whether, at least until we come to the games of incomplete information, we will be assuming that all the players know that they are players and they know who else is playing the game. That is the first thing. Second thing is, you can call it as a competitive setting, or a slightly different way of explaining the same thing is that the actions and the strategies of one player or each player affects all the other players and they are aware of it. So see, if you are taking an action and the other person doesn't even know that your action is going to affect them or vice versa, then you cannot call it as a strategic game by our definition. Somebody else may call it as a very nice game, very nice ploy or whatever, but in this particular series of problems, we will not call it a game. We will call it a game only when all the players know that they are players. And as a player, so if you take any game, for example, like a chess or poker or any other game you want, like tennis, for example. So you're not just playing against the wall, right? You are playing, even if you're playing with a machine, even if you say play chess on your mobile or whatever, the computer is the second player, right? You're not playing against nobody. You're not playing by yourself. So that means that, whatever you're doing, plus whatever the other person is doing, both decide what the outcome will be, what your payoffs are going to be. The term payoff is used very, very commonly in game theory. The meaning is simply what you get out of it. Payoff is your profit or your utility or, whatever the good thing you're getting out of it, which could be anything. It could be money, it could be your goals being achieved, it could be something you want to have. whatever it is, we are going to use this word payoff to characterize all of those things. And those, what is a payoff in a game will be different in each game, but each game will have a payoff. And we assume that in all these games, all the players want to maximize their payoff. They want to maximize their utility or profit or payoff. Payoff is the general term. Some games it may be profit, like if you're talking about firms or something, investment or something like that. And in some games it may be utility. Utility is a term used mostly in economics. I'm not sure if it is used so much in other subjects, but in economics management we use the term utility. Utility is nothing but your kind of like a way of saying how happy it makes. That is your utility. Happiness is a very abstract term. Utility is a very well-defined mathematical thing in the field of economics and game theory. Next is that there are a set of rules to the game, and usually these rules will be either explicitly spelled out or it will be obvious in some other way in the game when you read the problem or when you read about the game. And all the players are choosing some actions or strategies. It's not like somebody else is choosing for them or it is just happening beyond their will or something like that. They are all choosing their actions and strategies. And one of the key things in all the games, at least initially, which you will study is, first thing is you will need to understand what are the players choosing. That is the strategy, because sometimes people get really lost in the beginning in game theory. They don't know where to start. So when you are starting with analyzing a game, this is where you will start. First thing, you will identify all these key elements of a game. Whenever any problem, no matter how complex is given to you. First thing, who are the players? Second thing, okay, let's assume that they know that they are players and they are aware of it. Second thing is, what is their payoff or utility in different settings in the game? Third is, what are the rules of the game? Or fourth, whatever you want to call it. And what are the actions or strategies which they are choosing? So these four elements, I would say, are what you have to look out for. It is not just the definition of the strategic game, but these are the things you are going to always look out for whenever any problem of game theory is presented in front of you. Okay, so now there's a few assumptions also which we have made over here, which we have not spelled out in this because not all games will have these characteristics. Nevertheless, these are some assumptions which we are making currently, and it is a good idea to understand what are these assumptions. First assumption is that of rational preferences. What do I mean by rational preferences? So what I mean by rational preferences is that firstly, each player wants to maximize their utility. They are not some sort of, a charitable trust or some somebody who is living on the fringes of the society or who's living in a silo somewhere in the mountains. We're not talking about those exceptional cases. We're talking about cases where each player is very clear that they want to maximize their payoff, whatever that payoff may be. So, in some cases, preferences themselves can be altruistic. So even in an altruistic setting, you know that altruistic element, altruistic meaning you care about the happiness of somebody else also, right? So even that is actually maximizing your happiness or your payoff. So you are very clear that you want to maximize your payoff. There is no exceptional circumstances here where person doesn't care about their payoff. Okay, so they do care about their payoff and they want to maximize it. Always. Second thing is that, the principle of transitivity, you could say, where if there are 3-4 things which the players are choosing between. So if they prefer A to B, or let me actually write in the preference sort of style. Oops. So if A is preferred to B and B is preferred to C, A is preferred to C. This falls in the category of preference relations in set theory, and also I think we studied in microeconomics. So I'm not going into the whole study of preferences, but just the basic thing that if A prefers B, if the player prefers A to B and B to C, then they will prefer A to C. It cannot be they prefer C to A. So those are not rational preferences. These are rational preferences. In assumption, these two you can say go within the whole domain of rationality. The second assumption, at least for the first few weeks, will be complete information. So by complete information, I mean this is the proper official term or technical term. By complete information, we mean that all players know their players. All players know that they are playing the game. They know what their payoffs are, and they know what the other players' payoffs are. So maybe two players, there may be more than two players. All players are aware and they are clear that, first of all, that who all are the players and what the payoffs of each player is for every strategy. So everybody knows everything. That is what we call as complete information. Okay, so these are two broad assumptions which we will be making in the first few class of games. There will be some cases of Bayesian games and things like that, which we will come to in the later weeks. There we will not be following the complete information thing. We'll relax that assumption and we will study some cases of incomplete information and all that. But that is, until we get there, we will assume complete information. So the next thing is the notation part. So, we have there's a whole lot of notation in set theory for game theory, but I'm only touching upon the very basic things here. So for example, like we will denote say suppose there are n players. Ith player playing, for example, then is playing. All other players are mentioned as minus I. It's something which is slightly weird in game theory. Not exactly weird, but it is just a mathematical way of saying everybody other than I. When we say minus I, so say suppose you're writing strategies, we generally denote strategies as actions or strategies. So say suppose you have actions and strategies of players. So I is action of player I, and A minus I is action of players except I. Mostly we will be discussing two-player games in the beginning, but there can be multiplayer games also. What is the outcome matrix? So let's say we write the utility. So when we're writing the utility, we write utility of which player I. So that is the subscript for utility. When we are writing the utility, we will write first the strategy or action of player I, and then the strategies or actions of other players A minus I. Okay, U donates the utility, and in different cases, in different circumstances, utility could be the profit, it could be the amount of apples you have, it could be how much military victories you have. It could be anything. Okay, but your utility is a general term we are using here. It is a general term for the payoff. Players we generally denote as P1, P2, but you could call them whatever you like. So suppose I make it like this, and this is P2. So here, what we will do is, this is say strategy 1 of player 1. Let me just let's say A, B, X, Y. A and B are the strategies of P1. X and Y are the strategies of P2. So here what we are writing, we will write payoffs like this. Something, comma, something in each box, right? Just explaining these basics because those who may not have much idea of game theory, these things feel a bit bogging down kind of thing. The first thing here in this box, what we are writing is the payoff of player 1 when he is playing strategy A and P2 is playing strategy X. Okay. So say suppose this is some value 2. And in this box, what I'm circling now, or in this place, what we are writing is the payoff of player 2 when player 1 is playing A and player 2 is playing X. Say suppose it's 4. So this is how we write the outcome matrix for different strategies and different players. So this I made as a 2x2 thing, but it can be for any number of players. So, you just keep adding rows and columns. So when you are doing things like Bertrand competition or Uno competition and things like that, you may be given an example of, price and quantity, like you have a whole set of prices, a whole set of quantities, things like that. So you may have a much bigger table. Please don't get scared. It's just representation. It's not actually difficult. It's just a way of representing it. And once you get familiar with the representation styles, it really isn't that difficult. Now, similarly, this part, let me write it in some other color. So this is the orange one. Here, the first place is the payoff of player 1 when he or she is playing strategy B and player 2 is playing strategy X. I'm sorry. Okay, no, actually, what you're saying, I think I have this. Sorry, this is 2 and this is 1. Actually, I used to follow a different notation. That's why I kind of messed this up. But anyway, so yeah, you're right. You mentioned something in the chat. What I didn't exactly read the whole message, but yeah, I realized that I put 2 and 1 opposite. So sorry, please excuse me for that. So P2 is the columns and P1 is the rows. Okay, that is a general convention. You can write it in a different way because it's not exactly clear, and most of the time, which is P1 and which is P2. And if you see most of the books like Osborne and all, they don't mention P1, P2, anything. They just write A, B, X, Y, especially if it's a symmetrical game. So, but forget about 1 and 2. The main thing is that this one, say suppose the payoff of 2, is for the player who's playing strategy A when he is playing strategy A and the other is playing strategy X. Okay, I hope it is not confusing. 2 is the payoff of the column player when he is playing strategy A and the other player is playing strategy X. 1 which is 2, you can kind of figure out as per your preferences. I know that they are following the convention of 2 and 1, so let's do 2 and 1. Just change that to 2 and 1. Okay, I hope that addresses your doubt. Okay, so on and so forth. This is just a brief about the notation. Then we will come to the concept of Nash equilibrium. So before we come to the concept of Nash equilibrium, let's first understand what is an equilibrium, because this is something a lot of people have a lot of confusions about. What is an equilibrium? All these three, do they all three represent an equilibrium, or only 1 or 2 of them represent an equilibrium? What do you guys think? Hence, what is an equilibrium? Does anybody want to attempt to answer?
They represent different kinds of equilibrium.
Yes, great. So what type of equilibriums do you think they're representing? All of them.
Like one has the tendency to reach back to the one which is inverted in green color. So
sorry, could you just repeat that? Your voice is breaking actually.
So the one in green color, the equilibrium which is there in green color. So if the position is moved away from the current equilibrium, it has a tendency to reach back to the equilibrium. Whereas
Yes,
the
great.
red one is not like that. And the line, if it is moved away from the equilibrium, it again reaches another equilibrium.
What is that called? What are all these three? You're correct. Do you know the names for all these three?
One is stable equilibrium, I think.
Yes, good. So the green one is a stable equilibrium, red one is an unstable equilibrium, and the gray, that flat surface, is neutral equilibrium. But they are all three equilibria. So sometimes people get confused and they think that the green one is an equilibrium and the gray one is not, or the red one is not. The fact is all three are equilibria, but they're all different types of equilibria. So there are different types of equilibria, and this is sort of like a small footnote or something you can say, which you need to remember. You may not use it immediately in the first few examples of game theory, but it will be useful later on when you come to slightly more complex situations. So what is the definition of an equilibrium then? Can somebody give me the definition of an equilibrium based on what we discussed so far? Anybody wants to attempt to answer?
A steady state or
Somebody else, you already answered.
okay.
I guess it is a balance of something in action, equal forces at work.
Something like that. Okay, I'm asking, I mean, you are correct, but I'm asking for something even more fundamental and simple. Simple definition.
Equally opposing forces at work, I guess.
There will not necessarily be forces always. There may be situations when there are no forces also.
Thank you.
So, okay, I will give 1 more minute if anybody else wants to attempt to answer. Okay, so an equilibrium is basically when, any object, any situation, any variables, any parameters, anything, when it retains its state absent any changes in external factors or external parameters. So you may have an equilibrium of anything, right? It can be an equilibrium in terms of the kind of revenue you're drawing. It can be an equilibrium in terms of the the pollution level in the city. It can be an equilibrium of the kind of extraction of some resources. It can be an equilibrium in terms of like she was saying, some push and pull kind of force. So it can be any kind of an equilibrium of anything, not just a person or an object. It can be an equilibrium for any defined variable or any defined quantity. Okay. The main thing is the equilibrium is that particular quantity or that particular object or that particular agent retains their state absent any changes in any other factors or parameters. External, you can say external to the object, but when we say external, it kind of means the same thing. So I hope that idea of equilibrium is clear to everybody. So for example, in the red one, if we change the external factors, like if we move the ball, what we mean by changing external factors is if you move the ball, you're changing the external forces, right? In that case, it will not come back to its original state. But if you do not apply any force, if you do not move the ball, if you don't do anything, it is going to remain there for eternity. If you keep this setup in vacuum, or if you keep it, in some place where there is no other disturbance from anywhere, it's going to remain there forever. Right? Same thing with green. The plus we have in the green bowl is that if you move the ball, it has a tendency to come back to its original spot. Even in this situation, if you don't move the ball, it will remain there. And you can say that it's the same thing even with the last one. It's a neutral equilibrium, means if you move it to some other spot, it just remains at the new spot. It achieves a new equilibrium. Right? It doesn't have any tendency to either move away or towards anything, any particular state. Wherever you keep it, it's going to be in equilibrium over there. So it's in kind of like a perpetual equilibrium. So these are different types of equilibria. And I know this is not covered in your lectures per se, but this is a concept which Professor Vimal has himself discussed in the classes on game theory. He is my co-supervisor. So I wanted to just include this in the class, or it'll be a good thing. Okay, so now we'll play a game. Okay, we'll play a great game. It's a game which I have basically borrowed from the lectures of Ben Pollack. This is a separate YouTube series of Ben Pollack on YouTube. If you want, you can check it out. If you have that kind of time. Somebody's asking, there is no incentive to deviate. No, we are not talking about incentive to deviate here. Please don't confuse the two concepts. I know it is very tempting to call it that, but it is. We are not talking about incentives at all. Let's just go back to that picture once again. We are not talking about incentives here to deviate. We'll come to Nash equilibrium, which is why I wanted to first discuss equilibrium before we go to Nash equilibrium. Nash equilibrium can be any of these kind of equilibriums. Okay. Why there is no incentive to deviate in Nash equilibrium, we'll come to it. Let me just first get into the whole thick of game theory. But this, what I'm talking about is any change in external factors. I'm not talking about incentive to deviate. Okay, so this is a great game, like I said. This is a game which Ben Pollack introduced in his class. I mean, it's an example of a classical game, but I'm just taking it as is what he took in his class. So I want all of you to pick one of the two letters, alpha or beta, and please message it only to me, not to the whole class. Let me see if this chat has a feature of messaging only to me. I don't think it does. No, it doesn't. Okay, you don't have to message it to me then, since that feature is not there. But I guess you can just write it down because we're not playing this for any kind of a grade or something. So, somebody saying something? Yeah, chat is. Oh, you're not seeing any. Are none of you seeing any other messages by anybody? All the chat messages, are they coming only to me, or is everybody able to see everybody else's messages also?
I think we got a message saying I'm not seeing other messages.
Okay, so I think my understanding is that this is a chat common to everybody. So I don't really want to disturb that. So let's not do that. I just want all of you to just write down very quickly. I'll give you 15 seconds to play this game. Everybody, please write down one, alpha or beta, which one you're choosing based on the payoff table I have shown on the screen. Okay, this is the payoff you're going to get. Who your partner is right now, we don't know. You will be matched with the partner later on. So somebody has raised their hand. Is there a question? Kumar Pradeep, I think you raised your hand. Anything you were saying?
That was by mistake.
Okay, so please don't post your answer in the chat. That is the whole point. Please don't post your answers in the chat. Just write it down for yourself on a piece of paper. Okay. Can I say that everybody can now share their answers when you post all your answers? And please be honest. We're just relying on your honesty. It's just a game. Okay, it's not anything particularly. You're not getting marks for this, but. Okay, I think people are not understanding. Please write it down only for yourself on a piece of paper. Please don't post it on the chat right now. Everybody done writing the answer? Yourself in your own notebook or paper or something. Okay, so if everybody has finished writing, I want everybody to post on chat whichever whatever letters they have chosen. And I will make a match of different people. And let's see who gets through. Now, can everybody please share their answer in the chat? Doesn't have to take a lot of time. if people are not understanding this to be difficulties. Is everybody clear? Has everybody clear what they have to do? Okay, some people have shared. So there are, I think, 8 people on the right. So there should be even number of pairing. So I have, you don't know who is paired with whom. I'm pairing you guys. Okay. All right. So let's see who has answered what. I'm just writing your answers, whatever you have said. So you can see from the chat now how many people have chosen what. Okay. Why did a lot of people choose alpha? Does anybody who chose alpha want to answer why you're choosing alpha? I'll come to that part. Pratik is asking if there are strategies. Yes, there are strategies. That is what I'm trying to kind of illustrate through this game. So Chandana, I think you have not posted your answer. She's there on the Chandana, Subhash, Sri, Akshay. You guys have not posted your answer.
Mom, the chat doesn't appear. It says it's setting up. However, I have chosen
Oh.
alpha.
Okay, all right, thanks. Akshay, can you answer in the chat? I think Chandana has also not answered. Okay, so basically what we're trying to see is what people answer and why people answer what they answer. We will come to that in a bit. So let's have any one person who has chosen alpha answer why they have chosen alpha. Can you answer why you have chosen alpha? Ready?
I chose alpha, first of all, out of a random choice. There was no particular criteria. I did see what is there in it, B minus, B minus. And I thought that in case I'm paired with someone who is a beta, then it would be a good match. It was purely a random choice.
Okay. Anybody else wants to answer?
I also chose alpha because A for alpha and all that. But I did some. I mean, if assuming if I am the column player, then strategy of alpha, then that turns out to be. I mean, if I use game theory language, it turns out to be B minus is greater than C and A is greater than B plus. So I just thought
Yes,
probably
great.
that is the doctrine.
Okay, good. So that is, I was hoping somebody will come up with that answer. So that is what we were trying to discuss. So I did not want to speak too much about the game in the beginning because I wanted you guys to have the practice of interpreting a payoff table. This is how you interpret a payoff table. So the question is, as you can see on the screen, 2 players are asked to choose one out of alpha and beta. This is typically how you will write a strategy in the curly brackets. They are awarded grades based on what they and their pair pick. So that's why it's a game, right? There are 2 players, any 2 players. You don't know who your player is right now, but you know what the payoff of you and your player will be, and you know what all your other player can choose, right? Now, what is your payoff in this case? The payoff is the grade. You want the highest grade. We are assuming rational behavior, right? Which means each player wants to have the best grade, and of course, the grades are ranked as A, B plus, B minus, and then C, right? So everybody wants to maximize their grade. And this is what your payoffs are going to be based on what you and your pair choose, right? So now, since you guys have played the game, you can sort of have a better idea of what your thinking process can be or should be, or how you can mold your thinking process. It's okay if you didn't get it sort of right the first time, but I'm just trying to get you to think about how to think about it, okay? Because game theory is nothing but a training in thinking. How do you approach the problem? How do you think about it? So, for example, what this game, the way this game is set up, like he was saying, if you're, say, suppose you're P1 and you're choosing alpha, you get B minus when your opponent is playing also. And if you are choosing alpha and your opponent is choosing beta, you get a C. So B minus is better than C, so you choose an alpha. If you choose an similarly for the other case also, like, if you're choosing alpha and the opponent is choosing beta, then between alpha and beta, you are getting better for alpha. Okay, let me just draw it here because speaking kind of can be confusing. So suppose you are player one, okay, your partner, this is your pair. Right? So when you are choosing alpha and your player opposite is choosing alpha, you are getting B minus, sorry. And if your partner is choosing alpha and you're choosing beta, you're getting C. So which is better? B minus is better. Now, if your opponent is playing beta and you choose alpha, you get an A. Whereas if you choose beta, you get a B plus. So A is better. So in both the cases, whether your opponent is choosing alpha or your opponent is choosing beta, you are getting a better payoff for choosing alpha. Similarly, now if you think from the point of view of player P2, it's the same thing. If they choose alpha here, they get B minus. Whereas if P1 is playing beta, they get again a better payoff for alpha. So you can see that alpha here, because the box, you see basically the box in which the persons have their strategies in circles, the best response, and hence it is the Nash equilibrium. Now what do I mean by circles? So what I do is that when I look at my strategy, or let's do it the other way around. If I look at the opponent's strategy, so suppose alpha is the other player's strategy. Okay. So for that strategy, what is the payoff I'm getting for alpha and what is the payoff I'm getting for beta? Alpha I'm getting B minus, for beta I'm getting C. Between these two, which is higher, which is better? You circle that one. So I've circled this one. I'll delete this annotation, by the way, it's becoming untidy, but just for explanation purpose. And for your opponent, now let's see what the opponent is thinking. For the opponent, if P1 is playing alpha and they are playing alpha, they get B minus, and if they are playing beta, they get C. So B minus is better. Similarly, if they are choosing, you can do the other way around also. If P1 is playing beta and P2 is playing alpha, they get a better payoff compared with beta. So this is also better. In this case also alpha is better. So since alpha is the best response for P1 and P2, alpha is the equilibrium. And we will come to dominant strategies. We will see that alpha is also the dominant strategy. Okay, so what is the Nash equilibrium basically? I wanted first to illustrate it through a game before we come to the actual Nash equilibrium. So okay, so a Nash equilibrium is when all the players are playing their best responses to each other. Intersection of my best response to all the best responses of all other players is basically the Nash equilibrium. When you are playing any strategy, I will choose my best response, the best responses to all your strategies, and you choose your best response to all my strategies, right? And that intersection, or that point where I'm also playing my best response and you are also playing your best response, is the Nash equilibrium. What do we mean by best response? Best response is the response or the strategy or the action which gives you the highest payoff for the given, strategy of your opponent or the other player or players. Now, we will come to all these points a little bit through other examples also, but just to understand what makes a Nash equilibrium, first of all, in a Nash equilibrium, no player has any incentive to deviate. And why is that? Because in a Nash equilibrium, if you deviate, it is not just you who is deviating. Your other opponent will also deviate, and that will change your payoff. And payoff you will get after deviating will be lower than the payoff you're getting in the current setting, which is why we say there is no incentive to deviate. I'll show this through another game if it is not very clear. It's self-enforcing. Why? Because like this first point kind of leads to the second point. Self-enforcing means the same thing. that if you don't want to deviate, you're happy with where you are, then it becomes self-enforcing. You don't need to enforce it through a contract, through a legal something or whatever. It is not always Pareto optimal also, because what is Pareto optimal actually? Pareto optimal is when you cannot improve the payoff of both the players simultaneously by making a change. For example, if I choose the strategy alpha beta, right? Let me go through this previous game. This particular game, if say suppose A chooses P1, if P1 is playing alpha, if P1 is playing alpha and P2 is playing beta in this box, can improve the you can improve the payoff of P1, but it is worsening the payoff of P2, right? This is what we call as Pareto. In this particular case, it is Pareto optimal. It is not going to be the case always, is what I'm trying to say. Let me clear the margins here. Okay, so what I'm trying to say is that Pareto optimal is a place where, say, suppose this is a Pareto optimal payoff 2. If you deviate from here, you may increase your payoff, but then the other person's payoff is going to be decreased. There is no way you can make any change from here. So suppose you get 3, 1, you get 4 and 0, right? So 2, 2 is a place from where you cannot move without any reduction in payoff of some other player also. For example, if you can move from 2, 2, 4, 4, this is not a Pareto optimal place then, because you can improve the payoffs of both the players. Clear? Is this making sense? If you're in a place from where you can move to another strategy such that the outcome or the payoff of both the players can be improved, then that place is not Pareto optimal. Whereas if you are in a place from where you move and you increase your payoff, but the other player's payoff becomes lesser, then you are actually in a Pareto optimal state. So Pareto equilibrium or Pareto optimality is a separate concept. And sometimes Nash equilibrium may be Pareto optimal, but it is not always true. It will not always be the case. You have to be careful about this, because sometimes you may not be asked a Nash equilibrium, but you may be asked whether the response itself is Pareto optimal or not. So this concept is important. And a Nash equilibrium doesn't always exist. This is something which may seem strange considering we are studying game theory, but that is how it is. You may not find a Nash equilibrium in every kind of a circumstance, every game. Okay, so I'll just quickly go over the prisoner's dilemma, because this is like the classical game. So they are the two agents, so the two players are prisoners. They both know that they are going to get some sort of a prison sentence, and what they say is going to decide not just their own prison sentence, but that of the other person also. They both want to get the lowest sentence possible, or if possible, go scot-free. They cannot communicate with each other. This is an important set of rules in this particular game. And their actions and strategies are basically either to confess or to deny. They don't have any other option. There's no third option. Okay, this is the setup of the prisoner's dilemma, and it is a classical game because it has been done to death, like every other law show or any crime drama, any police show or anything. You will always find an example of this. In fact, you can find an example of this even in less aggressive, less formal settings, where say things like, there's a, I don't know how many of you watch all these TV shows, but there are many TV shows like Seinfeld, I think even Friends, where many times there are situations which are actually a good example of prisoner's dilemma. So I would encourage you to find these kind of examples in daily situations, in movies, TV shows, whatever you guys watch. This is an example of prisoner's dilemma. This, you can see, is the game table. And this particular game, what happens? Let's quickly go over it before we go for the break. So in this case, say suppose again put 1 and 2 opposite, right? Let's put it. Yeah, I made this before, so that's why. Do it like this. This is a symmetric game, so it won't make a huge difference, but since this is what everybody has been following, I'll just keep it that way. So, say suppose, player 1, or let me not do this. First, I want you guys to quickly attempt this on your own without looking at the video or lecture slides or anywhere. I want you guys to first quickly find the Nash equilibrium. Give you 2 minutes. This is a game which has already been studied in the class, so it should not be too difficult. I think I may have changed the payoff a bit, but it is not too much of a difference. The basic setup is still the same. So you to please try solving it, and then I will solve it in the class. Okay, so what is the Nash equilibrium? All solved. Tried solving.
I think it should be D, deny.
How did you get that?
I looked at -10 and 0.
And
That would be the lowest sentence. And since prisoner 1 is doing it the first time, the payoff will be more for prisoner 1.
sorry, what? This is a simultaneous move game. Okay, so this is another point I think I should maybe write it in assumptions. In all the games we are discussing right now, they are all simultaneously played. As in both the players are choosing simultaneously. So, it's not a step-by-step process. That first one will choose it, next second one will choose. Those are extensive form games which we'll come to later. As of now, all the two are in two separate groups, and they're both being dealt with by separate thought. And both do not know what the other is saying, and they both have to choose without knowing what the other person is saying.
One doubt, what does 1 represent here?
1 is some kind of payoff you get, utility or happiness you get from going scot-free.
Like
Madam.
-5
It's
means
again- Meaning
Am I
-5, yes. -5 is the negative of like what you say as utility versus disutility, right? So if he is getting, say, 5 years of prison sentence, that is -5, right?
5 years of prison sentence is -5.
Yes.
Okay.
10 years of
Okay.
prison sentence is -10. Okay. What
So
I
one
put
is-
in deny. If both deny, one you can say it is not about prison sentence, but you can make it. I don't want to make it 0-0 or something. I've just changed the payoffs, so it is a different setup. But one you can say maybe 1 year they get some award or something, whatever you want to call it as.
Okay. Thank
Because
you.
I'm showing the payoff in the table, not the sentence, but per se.
Thank you.
So this is a good question actually, because it is important to remember what you are representing on the payoff table. Because sometimes it may not be just the exact number you are given. Sometimes it may be, like here I'm mentioning the utility. Okay, let me write that down.
Madam, if
So,
Madam, if 1-1 is the utility, then in this
yes.
condition, when both prisoner 1 and prisoner 2 deny, then if you choose any other cell, there is always a lesser utility for both of them. So I think this is the Nash equilibrium where no one gains at least.
Okay, but how did you arrive at this Nash equilibrium? So I want to first understand how you arrive at the Nash equilibrium, not what alone is the Nash equilibrium. Like, okay, you mentioned what you assume. So let's work this out. That's why I wanted everybody to attempt it first, because without attempting, if I just tell you what to do, then you kind of don't catch the thinking process. Okay, suppose I'm talking about prisoner 1. Okay, now prisoner 1 is thinking about what happens when the prisoner 2 is playing confess. Okay, first let's discuss that scenario. I am prisoner 1. There is a certain prisoner 2 with whom I've tried to attempt a bank robbery or whatever, and prisoner 2 is being interrogated in a separate room. Okay, prisoner 2 is saying, prisoner 2, I am assuming prisoner 2 is going to confess. What happens if the other person, if I think the other person is confessing, what happens for me? If I confess, I get -5. If I deny, I get -10. So what am I going to do? What am I going to prefer? -5? Or no? Correct. Okay. Now, if the prisoner is 2, I'm assuming is going to deny, then what do I get? If the other person is going to deny, I get 0 if I confess, and if I deny also, I get 1. So 1 is the better response for me if the other person is denying. Okay. I think I may have put the payoffs wrong. Okay, let's keep going forward and see what happens. What happens now if say suppose I'm thinking from the point of view of prisoner 2. This so far we have discussed strategy with prisoner 1. Then we go to prisoner 2. So irrespective of what comes out to be the Nash equilibrium, or whether there is a Nash equilibrium or not, so I may have just tried to confuse you also. Maybe there is no Nash equilibrium in this game. My question is to find out how you arrive at the Nash equilibrium first, because I don't want you guys to just rote learn and remember the Nash equilibrium, or just look at the numbers and guess that maybe this should be the Nash equilibrium, or okay, this looks better than this, and maybe this should be the Nash equilibrium. No, there is a step-by-step process you have to always follow to find the Nash equilibrium. Are you getting me? It is not based on what looks nice to you. It is based on what you will arrive at without any assumption, without any biases, in a step-by-step way. Now let's look at prisoner 2's position. Say suppose now the prisoner 2 is evaluating what he should do or she should do. If prisoner 1, I say suppose prisoner 2 thinks that prisoner 1 is going to confess, is the best strategy for them to do. They confess and prisoner 2 confesses, they get -5. If they deny, they get -10. So -5 is lesser than -10. So I'm going to go with -5 for prisoner 2. Now prisoner 2 is trying to evaluate what they will do if the other guy is going to deny, right? Now if prisoner 1 is going to deny, then if prisoner 2 confesses, they get 0. If they deny, what they get is 1. What happens in this particular game? What do you think we got?
So are you saying we are getting 2 equilibriums?
Yes, exactly. So I've set this game up because I wanted to illustrate how just a slight change in the payoffs, even in the classical game, can completely change the game.
And the classical,
so
I think it was -1.
Yes, in the classical game, yes, so that's what I'm trying to tell you, that you should not rote learn a game.
Yeah, okay.
Because if you rote learn the game and you rote learn the payoffs, you will assume कि जो था class में वही होगा, and question में हो सकता है कुछ different हो, right? What I've changed the payoffs from what is there in the live session. I don't know if you noticed, but this is not the payoffs in the live session, which is why I think some people asked me in the beginning, why is there one here voting with me? So in this particular, this is also prisoner's dilemma. Okay, we have not set up a separate structure for the game. We're following the same rules, the same strategies. Only the payoffs of the two prisoners are different. So in this particular game, if I change the payoffs, I can bring it back to the same question you had in the class. But what I wanted to illustrate is, if there is a change in the structure of the game, in the payoffs, you may get a different result. So please don't ever rote learn a game. Okay. So in this particular game, you have this and this, both are Nash equilibrium. So which means that the cops have not set up the game properly. If the cops set up this game like this, say suppose I'm a new cop in the police department, and this is what I offer to the two prisoners. And So there is basically a 50-50 chance that you may end up with a confess equilibrium, or you may end up with a deny equilibrium. Why will I want deny to be the case, right? So I have to offer them something different, because you see all this -5, -10 is what the cops are offering to people, to the prisoners, or to the people who have captured. Now, they don't have enough evidence to convict these people. That is why you are having this prisoner's dilemma. I'm not repeating a whole lot of the things to discuss in the class, which is why, I've omitted many of the other founding information or something. But this is basically your classical prisoner's game, but with a change in the payoffs. So here what happens is there are two Nash equilibrium. -5 is corresponding to confess. 1 is corresponding to deny. So that means that new cop needs to change the payoff for deny, this one, and need to make it maybe something else. Like, if you make this as -2, then you will get only one Nash equilibrium, which will be confess. This is something like this is there, I think, in the live class, where if they both deny, they get a lighter prison sentence for just theory or some impersonation or some smaller charge, because they cannot be convicted for the real charge or something. But they don't actually get 1-1. So if I'm a new cop, I would want to change this to this kind of thing. This is clear. The method you use to arrive at a Nash equilibrium should be clear to everybody. Because I can discuss as many examples as you want, but unless you have clarity on how to go about the question, you can keep getting confused. Okay. See, somebody asked. Okay. So let's come to the point of dominant strategies. Dominant strategy or strategies are very interesting and very common thing in all kinds of games. A dominant strategy is very simply, or you can say a strictly dominant strategy is one which always gives a better payoff than some other strategy for, say, same player. If I'm player I, then for me a strategy SI star is strictly dominant if it always gives a better or a higher payoff than some other strategy SI prime for me. So this is the definition of a dominant strategy, which means that this dominant strategy may not be dominant for all my strategies. Remember that. For example, there may be some other strategy I had, suppose, is strictly giving me a higher payoff than I start. Okay. So what I'm trying to say is that in this particular case, is dominating I prime. Whereas in this case, sorry, SI start is dominating. So one strategy can be dominating over another strategy when that particular strategy gives me strictly higher payoff for all the strategies of my opponent. I'll just show you an example for this. But remember that a dominant strategy may not be dominant over all strategies. Okay, there may be some other strategy which gives me even better payoff than a size. Let's take an example. So I will just mute myself for a minute or two, and I want all of you, this is very simple, to please find the dominant strategies of player 1 and 2 if there are. If there aren't any, it's fine. But I want you to at least try to find dominant strategies. The payoff table is as it is. It is not too much to be explained. And I put player 1 and player 2 in the right conditions, so it's no confusion. So please use the method I have just explained to identify which strategies of each player gives a better payoff than the other person, than the other strategies. So please don't post the answer on chat just yet. Just solve it for yourself first on your paper or something. When I discuss it, when I ask you to share your answers, then you can post your answers in the chat. Just want to allow everybody time to do it on their own without getting disturbed by others. I think you have announced what you have to do. You would have made some kind of progress by now. So let's get into it. So can everybody post their answers in the chat? Whoever has solved it. What do you think are the dominant strategies of player 1 and 2, if there are any? Okay, one person has given the answer. Anybody else? Okay. So a lot of people got a lot of different answers. Let's see how we arrive at dominant strategy. Okay, what is the thinking process? So, like that's why I took a multiple strategy game. Like that's why I took a 4x3 matrix here, so that you get practice of thinking in these terms. This way, I just keep taking a 2x2 matrix. It kind of you are not drilling yourself. Okay, let's look at this game. Say suppose player 2 is playing the strategy X. Okay, let's talk about that scenario in which player 2 is playing strategy X and player 1 has to choose between A, B, C, and D. Okay. Now, if player 2 is playing strategy X, I will look at the first column, right? For A, I'm getting payoff 10. For B, I'm getting 5. For C, I'm getting 7. For D, I'm getting 3. 10 is the highest payoff I can get if player 2 is playing X. If I choose A, I get 10, which is the highest. Now, if player 2 is playing, say, Y, this is how you will proceed. You will first look at each strategy of the other player one by one and then flip it. Okay? Do it one by one. Don't try to do everything together. I know maybe you are very clever. You can do it all immediately by just looking at the table, but sometimes that may not work. Sometimes that can be a trap which the teacher has set for you. So don't try to do everything together. Go step by step. It may take a few minutes, but it's going to be worthwhile to spend those few minutes, because when you get the practice of doing that step by step thing, that step by step will only become very quick for you later. Now let's assume player 2 is playing strategy Y. Okay. Player 1 has the option of A, B, and C, A, B, C, and D. Now for A, player 1 gets 8. For B, player 1 gets 4. Sorry, 1 is a few minutes. So, yeah, for player 1 gets 8 for A, 4 for B, 3 for C, and 5 for D. So again, 8 is the highest of all these, right? So 1 is getting highest payoff for strategy A. Again, that payoff is 8. Now let's see what happens when player 2 is playing Z. Player 2 is choosing Z. Then at the payoffs of player 1 again. For A, she's getting 7. For B, 5. For C, 2. And for D, -1. Of all of these, again, 7 is the highest, which player 1 is getting for strategy A, which means that for strategy A, player 1 is getting highest payoff amongst all other strategies. Every strategy of player 2. This statement clear to everybody? No? It is clear. Should I move forward? Okay. So is that a yes or a Y?
Yes, ma'am. Yes.
Okay, great. Somebody posted Y in the chat. That's why I was wondering. Okay, now let's look at it from the other perspective. Okay, from the perspective of player 2. Now let's look from the perspective of player 2. I suppose player 1 is playing strategy A. As player 2, what will they be getting? For X, they're getting 2. For Y, they're getting 3. For Z, they're getting 5. Which is the highest? 5, which they're getting for playing Z, right? Then, if say suppose player 1 is playing strategy B, if they play X, they get 7. If they play Y, they get 4. If they play Z, they get 8. Getting the highest for Z, which is 8. Then you go to scenario where player 1 is playing C. What is player 2 getting? For X, they're getting 3. For Y, they're getting 2. For Z, they're getting 9. What is the highest for these three? They're getting higher payoff for Z. Let's look at the last scenario where player 1 is playing D. If player 2 plays X, they get 2. If they play Y, they get 2. If they play Z, they get 3. So again, 3 is the highest of all. Now you can see that in this column for Z or Z, 2 is consistently getting higher payoff for strategy Z for any other strategy of A. For every strategy of A, irrespective of whether player 1 plays A, B, C, or D, player 2 is getting the maximum payoff for Z, right? So Z is Z or C, whichever way you like to pronounce it, American or British. For Z or Z, they are always getting the highest payoff. And that is right. A is the dominant strategy for and Z is dominant. Okay, my handwriting is really bad, so I'm going to take these annotations later on. This is just for explanation purpose. You don't actually need it. I will see. I'll write it separately or something that knows the solution. Is this clear? So now you can see that in this particular box, both the players are playing the dominant strategies, A, Z. Therefore, A, Z is the Nash equilibrium. Any doubts? Is this clear? Okay, I'm assuming it is clear. We take a short 5-minute break now. And in the meantime, I will just leave this on the screen. This is a game of rock, paper, scissors. And it's a very, very common game. Okay. I think when we were kids, a lot of people play this game to choose who is the winner or who wins, something like that. So I want to find out if there is a Nash equilibrium and or if there is a dominant strategy in this particular game. So please use the methodology I have just explained and find out if there is a Nash equilibrium. If there is no Nash equilibrium, that's also fine. But I want you to go through that process as I explained. Rock, paper, scissors for both the players, 1 and 2. Okay, so see, this is a symmetrical game. So even though I have put P1 and P2 like this, sometimes the way, please don't post your answers yet if you have solved it or if you think you have solved it. I'm just explaining the question right now. Just take the few minutes I will give you when I mute myself to solve it, and then I'll come back and discuss the answers. In this kind of a game, sometimes this P1 and P2 will not be mentioned at all because it's a symmetric game, same strategies for both the players. So this P1, P2 is kind of redundant, but I've just kept it here for the sake of clarity. Somebody has raised their hands, yes?
So, ma'am, just after the break, if you can also focus, I don't know whether you can. There are some sums in the assignment which don't have any numbers in the payoffs.
Yes, I will come
There are
to
some
that, but
variables and
I will come to that. I will come to that. Don't
directionally
worry. I have.
you can inform. And there is something shown on auctions and attrition. So, is there? Don't specifically mention about that, but is it out of the syllabus or is it in the syllabus? Maybe some kind of a direction.
So auctions actually is the game they have given as a simpler game. But we will discuss auctions in more detail also later in the course. But what they've given right now is a much simpler game. So I will take up at least 3 more games. Maybe if we are short on time, I will leave the simple one for you to solve.
Okay. Yeah.
So I'm not allowed to discuss the question from the example.
No,
but I will
don't
take
discuss the
separate,
question.
Yes,
Yeah,
I
maybe
will
some
take up
directionally.
that.
Yeah.
Yes, I will take up that class of questions so you can understand. So let's just quickly do this, and then I will come back and discuss. I have more complicated questions also, but this is the first class, so I didn't want to overwhelm everybody. So I wanted to first make sure you understand the process of arriving at the Nash equilibrium and dominant strategy. So I will just mute myself for a few minutes. Please solve this, and then we'll come back and discuss the rest of the questions. So we discuss this. Anybody solved it? You can post your answers in the chat. Please solve it. Okay, good. Yes, one person has, I think, solved it correctly. Yes, great, wonderful. So I think now everybody has gotten the hang of it. So I wanted to give this game because this is a very good example of a game which is a game. It is not that it is not a game. It is a game, but it does not have a Nash equilibrium, and it also does not have a dominant strategy. That is why people use this game, because it is purely, like you cannot decide, you cannot pre-decide which is the best strategy for you when the other person is in between rock, paper, scissors. There is no clear cut rational choice which you can make every time. Otherwise, everybody would always win, right? That's why this is not a game with a Nash equilibrium or a dominant strategy. If you know that the other person is playing this particular thing, then maybe. So at least we haven't talked about mixed strategy games right now. So I'm not getting into that. Okay. So maybe we can come back to this game in the mixed strategy setting later on, whenever we do that in the course. In the pure strategy game, there is no Nash equilibrium and no dominant strategy. Okay. So I'm not going over it rigorously like I normally would. So if you guys want, I can just draw the payoff table again and share it in the class notes later on. But I hope since everybody got the correct answer, I'm hoping everybody understood how to do it. So now there are 2-3 more examples I have, but I think I will leave these examples for you to solve. And if you're not able to solve this, because this is the first class, so I don't really know what the pace of the class is going to be. I'm kind of trying to see how much I can cover in each class. This hog dove game, this I've taken from Osborne, Martin Osborne. It's an unsolved example, I think, in Osborne. So I would leave this to you to solve. If you want, I can post this. I will post a solution for this later on. Not now, maybe in a day or two. I want you to attempt the game. This is another game which is Humanities versus Science. So this is from Dikshit. And this is, I think, also an unsolved example in Dikshit. So please attempt it. This is very similar to the Battle of Sexes. Okay. If there is time remaining at the end of the class, I will come back to this example or hog dove game, whichever you guys like better. But I want to talk about 2 other games which I think are a little bit more important for you. And if we have time left, we will come back to the other game. So this is the next example is the Battle of Bismarck Sea. So this is an actual game which happened in real life in World War II. Okay, this is, I won't go too much into the history of it, but basically there were the Allied forces. We had the Air Force, Allied Air Force. And then on the other hand, there were the Japanese Armada. They had ships, warships. And they both had to traverse across the island of New Britain over to New Guinea. Okay, and there are 2 routes which they could take. One is the northern route. You can see the diagram. This is taken from this particular website, but this game is a well-known game. I just took the pictures and the game setup from this website, but this Battle of Bismarck Sea is a very commonly known game. So this is a game of conflict, and I want you to understand how to think about games of conflict. It is actually a very simple game, but just for you to get comfortable with the idea. So there are 2 routes. There's a northern route and there is a southern route. Southern route has clear weather. Northern route has stormy kind of weather. Traversing along both the routes is going to take 3 days. Now, the Allied forces have air force. Okay, they don't have anything on water. And they only have air force, and they are going to use air force to do the reconnaissance of these ships. And based on how they can find the ships or how quickly they can find the ships, they're going to bomb those ships. That's their plan. And what the Japanese want to do is, of course, they know that the Allied forces have air force cover in this region. So what they would want to do is they want to avoid bombing as far as they can. So this is the setup. This is the rules of the game, and this is what choices they have. So you can see the game table has been illustrated in the form of this 4 diagrams. I will just explain what this game table means. If you want to read it in detail, it is there. It's at this link, which I put over here at the bottom. This link has a detailed description of this game. I'm not put it in detail, but if you want, you can read it. All right. So the Japanese are represented on the columns, the Allied forces on the rows. There is no one to just Japanese and Allies. What happens, what we mean by 2 and -2 is if the Allied forces are able to bomb the Japanese ships for 2 days, that is represented as 2. If they're able to bomb the ships for 3 days, that's 3. If it's mentioned as 1, that means 1 day. Okay, so far so clear. Japanese -2 means they face 2 days of bombing, so they're losing. They're facing losses, heavy losses. So this is -2. If they face 3 days of bombing, it's -3, and so on and so forth. So see, this is what happens. You can see the diagrams. It will explain to you. Now I have put the diagram and just the game table. The question you get somewhere, not just in this course, but somewhere else also. You may not get this kind of a clear diagram and this kind of a clear game table. All this may be explained to you in words, and you have to form the game table. This is something I want you to kind of start getting in the habit of drawing the game table, because the game table may not always be given to you. This outcome matrix, which we discussed, is what we call as the game table. So let's see what happens. So if see the first picture, where if the red, the red path that is drawn, that is the Japanese, and these tiny black airplanes like ants, which you see is the Allied airplanes. Okay. So now remember what is happening in this scenario is Allied forces are not putting all their planes in that particular route, but majority of their planes. Okay, so if the Japanese are choosing the north route and the Allied forces are choosing the north route. Remember, north route has heavy rain, stormy weather, turbulence. Okay, so what happens? The Allied air forces take some time to figure out where the Japanese are. Whether they can't see clearly. Remember, it's very hazy sky. It's not clear. Stormy weather. So they're able to they use Air Force for reconnaissance. They're able to find Japanese forces only after 1 day of surveilling the whole area. So they lose 1 entire day, and they're able to bomb the Japanese only for 2 days. So this is what's going to happen. So you have 2 -2. If the Japanese take the south route and the Allies are in the north route, remember the Allies are in the sky. There is stormy weather. Again, they take a long time to find the Japanese ships. Again, they lose 1 day of bombing. So they get 2 -2. If the Japanese take the north route and the Allies take the south route, again the Japanese are kind of hidden under cloud cover, and the Allies are also further away because they're on the southern route, so it's much more difficult to see the northern route from the southern. They get only 1 day of bombing. It's 1 -1. They both take the the south route. Everything's clearly visible. The Allies get 3 days of bombing, and Japanese face 3 days of bombing. So now, what do you think is going to happen? Anybody try to solve this? It looks like a very different kind of setup, but at the end of the day, we have sort of condensed it down to just the game table. So what happens? Let's try to solve. Okay. So suppose I'm looking from the perspective of the Japanese. Okay. This whole game table, because we're assuming complete information, remember, both Allies and Japanese kind of know this is what is going to happen, right? Because the sky, the weather, the route, visibility, everything is known to everybody. So they kind of understand that this is roughly what is going to happen. Because it's a real life example, I'm saying roughly. In the examples you get, it won't be roughly. If the Japanese are trying to consider the strategy, what we'll see is that if the Allies take the north route, the Japanese are indifferent. North route, south route, both are equal. the Allies take the south route, then the Japanese are better off choosing the northern route, right? In southern route, they get -3, so they'll choose the -1. Now, let's look at the bit from the example of the Allied forces. The if the Japanese choosing the north route, then what happens for the Allied forces? For north, they get 2, for south, they get 1. So 2 is better, right? Now, if the Japanese are choosing the south route, then the Allies get 2 for north and 3 for south. So 3 is better. So now what do we see? We see that the best response of Japanese and Allies is north-north, where both choosing their best responses. What happens? Both, it seems counterintuitive, right? That both of them will want to go through that thick, stormy weather of the northern route, but that is what actually happened. They both went through the northern route, and Japanese faced 2 days of bombing, and they took very heavy losses. So I'm not going too much into details of this example. It's a very interesting example. If you like, if you find this interesting, you can check it out. It's mentioned in the Dikshit book also, and that website is also explained it. And of course, you can go back and read it if you had a history buff. So this is a very different setting, so I wanted to take this example. But is this clear to everybody how we arrived at the Nash equilibrium? This is the Nash equilibrium. I'm going to assume yes. Now, we'll come to the example of the joint project. So now, let's assume we're taking an example of the Shelby brothers. I don't know if anybody, if you watched Peaky Blinders, we're taking an example of Tommy and Arthur from there. So say suppose there are 2 characters, Tom and Arthur, and we work on a joint project. Okay, here we don't have an explicit game table, so please pay attention. Say suppose Tom is making an effort X1. And for that X1, when he is working on that project, he has to pay a cost, you can say a personal cost or whatever, of 2x1, right? He's sacrificing time, leisure, something. For an effort of X2 by Arthur, he has to pay a cost of 2x2. But when they complete the project, they get a reward of X1 plus X2 whole square. And that reward is shared equally between both. Okay. Now, if they don't work, if both decide not to work, they can just go chill out or goof off or something. And they both enjoy some leisure, and they both get a reward of a payoff of 1 each, but they do not get any reward because they did not work on the project. So they did not get anything working on the project. The project remains incomplete, so they don't get any reward whatsoever. So here you have the condition that xi, meaning x1 and x2 both, can either be 1, 2, or now you have to find the Nash equilibrium. We have a similar example in your assignment. It is not this. Remember please that the payoffs are generally different. The structured functions, everything is different. It is not exactly this, but it is belonging to the same class of problems. Okay. I'm going to walk you through the whole methodology for this thing. And so we will work through, and hopefully you'll be able to arrive at the So can anybody tell me how we will make the game table for this question? Anybody wants to try? Sorry?
Plus 3 table. And then payoff will be reward minus cost.
Yes, good. So what we will do is make a game table something like I have put Tom, Arthur, like so, and see that instead of putting numbers like how we normally do, we're not putting numbers here. But what we do know is broadly what is happening, right? Now, if both are working, that means somebody is working on the project. So that means project is getting complete. So Tom gets a payoff of R by 2 minus C1 because the reward he is getting is R by 2 minus cost is C1. And Arthur is also working, so he also gets a payoff of R by 2 minus C2. If only Tom is working, Arthur is goofing off. He gets a reward of R by 2 minus C1, but Arthur gets R by 2. He doesn't pay any cost because he's not working, but he still reaps the benefit of the reward because it's a joint project. Irrespective of how many people work on it, if the project is done, both split the shares equally. Both split the reward equally. Okay. Similarly, conversely, you can say that if Tom is goofing off and only Arthur is working, then Tom gets the reward of R by 2 and Arthur pays C2 cost and collects R by 2 reward. So he gets R by 2 minus C2. There's a scenario here where if they both goof off, neither decides to work on the project, they both get a reward of one each. So as you can see that which one is the Nash equilibrium will depend on use of R by 2 and C1 and C2. So let's write the expression U1 is utility of Tom. Okay, if he works, if Tom works, you get x1 plus x2 whole square by 2 minus 2x1 utility of. So if he works with x1 plus x2 whole square 2 minus 2x2. In these cases, you can of course see that if you want, you can write out the whole expression. But if you want to leave it like that, you can just see that you just remove 2x1, 2x2. That becomes R by 2 in the scenario where they are not working but collecting the reward. So if suppose I want to maximize Tom's utility with respect to x1, we can do this plugging in the values of x1 is 1, 2, 3, 4 and see what is out to be the highest. We can also use calculus. So suppose if we maximize 1 with respect to x1, we take first derivative to see what value of x1 you're getting. It as 0 at all. So we have x1 square plus x1 square plus x1 x2 by d by d x1 or x2 x1. And this gives you x1 plus x2 plus let's set this as 0. So which implies that if x1 plus x2 is equal to 0, you get one extra now. Either it's maxima or minimum, we don't know yet. By symmetry, even if you do du2 by dx2, you will get the same kind of an answer. Let's do d2 u1 by dx1, you get 1, which means this is a minimum, right? So if x1, x2 is equal to 0, x1 and x2 sum up.
X1 equal to 2, no? Not 0.
Yes, that's what I just corrected. So if x1 plus x2 is equal to 2, then in that situation, you are getting a minimum. Because we are discounting, see over here, if you look at it carefully, I've given the scenario xi equal to 1, 2, 3 for this setup. Because for xi equal to 0, I've already mentioned what the payoff is.
I didn't understand when you said there will be a minimum. What is that for that?
Sorry, I didn't get your question. Could you repeat that?
You said something, we will get a minimum. How do you get that? What is that statement?
So you see, look at the second derivative. Second derivative is positive, it's minimum. the second derivative is negative, it's a maximum.
Okay. Okay.
So see, in this game setup, I have put xi equal to 1, 2, 3 because with the scenario xi equal to 0, it does not follow this function at all. There is a separate payoff, which I've already mentioned. This goof off is 1, 1. Okay, is everybody clear on the setup? And xi is only 1, 2, 3, then x1 plus x2 is equal to 0. Oh, sorry, is equal to 2 means x1 is equal to x2 is equal to 1. So for x1 and x2 both equal to 1, you're getting a minima. So which means that for any value of x1 or x2 greater than 1, you will get a higher payoff than whatever you're getting for 1. Now let's look at this a little bit. One more slide. Just need a little space. Okay, let me erase this part. I'm erasing
So
this part
how
because I
are we
just want to.
solving this now? You are just saying x1 equal to x2 equal to 1, but x2 can be 0 also, right? Or no? You're saying
Just,
because it is 0, then the payoff will be 1. Achha.
you answer your own question. I'm showing you the steps to solve it. Okay, in this particular question, we have just solved for x1, what values of x1 and x2 to get a maxima or a minima for. If this were already a maxima, then our problem would be solved here itself, but it is not. It's a minima, so we need to solve it further. Okay, so my question may be slightly more complicated than the one you have in your class, but the good thing is after doing this, hopefully that will look simpler. So this calculus part, I'm just erasing because there is no space for me to draw the table. It actually becomes a very simple table after this. So say suppose I choose x1 equal to x2 is equal to 2. Okay, this is the table. So this is work. This is work. This is goof off, and this is all symmetric. So I'm putting Tom, Arthur, you can put whichever you like. Okay. I suppose both x1 and x2 is 2. What is the reward? The reward is 2 plus 2 whole square by or I, let's say. Square is what? 16 by 2 is 8. I is 2xi, so it is 4. Or it is clear? x1, x2 both we're taking as 2, so the cost to both is 4, and the reward each will collect is 8, right? So both are working, what they will get is 4, 4. One is goofing off, the other is working, you get 8, the other. Control set here. Which is which, but I don't. So if Tom is working, he gets a payoff of 4. If Arthur is goofing off, he gets 8. Similarly, 8, 4, and you get 1 and 1. Okay. So in this case, what happens? Because xi equal to 0, we are not considering as a separate case because that we already took as 1 and 1. And this is the game table for the rest of the scenarios where x1 and x2 is equal to 2. This is now your one game table. Okay, now in this case, if I have to choose between working and goofing off, what do I get? If Arthur is working, is Tom better off goofing off or goofing off? If Arthur is goofing off, Tom is better off working. Similarly, if Tom is working, Arthur is better off goofing off. If Tom is goofing off, Arthur is better off working. The equilibrium you get here is W, G and G, both are Nash equilibrium. You can solve it for different in different cases and see what you get as an example. I think for x1, x2 both equal to 1, also you get a similar thing. I've forgotten what the solution came out to be. I set up this question a few days ago, but this is the basic approach you have to take. You're not given the numbers, you're only given a range in which the strategies can be. So first you set up the functional form of it, you set up the game table with the functional form. Sometimes just doing the calculus of maximizing payoff itself will give you the strategy, sometimes it may not. Like in this case, it did not. So now then, in this case, what we will do is we will take different strategies of players and make the game table for different values of the strategies. So I have solved it only this far. I don't know how much time we have left.
So are you saying that we have to solve it for x equal to
Yes.
1, 2, 3, and then
Yes.
between those three choose which is, depending on the question, choose the right answer?
You have
That's
to
how.
find out the Nash equilibria. That is the
So it
question.
might be different for 1, might be different for 2, might be different for 3.
Yes. Yes. So
Okay.
you will mention for x1 equal to this and x2 equal to this. This is Nash equilibria for x1 is equal to this, x2 equal to this. That is the Nash equilibria. So you'll report all the Nash equilibria separately. So you're asking what is the significance of Nash equilibria? I don't understand the question. Nash equilibria is, or Nash equilibrium is, happens in a situation and continues to happen. It's an equilibrium. I didn't understand exactly what your confusion is. So do you want to explain or expand further on that? No? In life, we would strive to get it. So this is not something you generally strive to get. It is more like something you end up with. Okay. A Nash equilibrium is, when you are in a situation where your actions affect others and others' actions affect you, you both end up choosing the action for which you are trying to always maximize your payoff given the other person's action. And the Nash equilibrium is what both the people will eventually end up choosing given the structure of the game, given what payoffs each person is getting for the game. So, I think that Battle of Bismarck Sea might explain your question, answer your question a little better. So see, in this particular example, it is not that they were trying to achieve a Nash equilibrium, right? They were both just trying to find out, looking after their own self-interests. The Allied forces wanted to do as much destruction as possible, and Japanese wanted to avoid as much destruction as possible, right? Nash equilibrium is the actions which you will both eventually end up choosing given this sort of game table, knowing what your alternatives are. So see, in most of the games you will face, there will not be infinite number of choices, right? There is a finite number of choices you have to make and a finite number of choices the other player is making. Given all the options you have and what you get out of those options, and given all the options the other person has and what they are getting out of the other options, knowing that both of you are maximizing your own self-interest, looking after your own self-interest, the end result you get is a Nash. Is that clear? I hope it's somewhat clear. I don't know how many of you have watched this movie, A Beautiful Mind, which is based on the life of John Nash.
Yeah, I've seen it, but I saw it before I started reading about game theory.
Okay, it's a very, it doesn't talk that much about game theory. Actually, it is more of a biopic on John Nash. But at least the initial maybe half hour or 45 minutes of the movie kind of talk about how John Nash came up with that theory. And he gives that example of a guy picking up a girl in a bar or something like that. The pub, yeah. So that is kind of like an example where he sort of illustrates the whole theory, what he's trying to say. That I'm trying to do the best I can. That guy is also trying to do the best he can. So this is what we end up with, right? I don't remember the exact example he gave, but I know that he gave an example of that kind of thing. So if you sort of just get comfortable with the idea of game theory, you will actually start seeing games everywhere in all movies and all kind of TV shows and everything. So yeah, there is another movie, I think, The Coldest Game, I think it's called. It's also about this, I think it's an American guy who's playing chess. He's playing a chess tournament in Russia during the Cold War years. They have to kind of make a decision based on, he's a very intelligent guy, of course. He's extremely intelligent. He plays chess. He's a chess grandmaster. And he's playing a Russian guy in chess game, but at the same time, he's also sort of like a messenger who needs to pass on some documents or something like that. And there comes a critical point where he needs to decide whether somebody in his own team, the US or Allied Forces team, is actually a double informant or not. And the way he takes that decision is also kind of very interesting. It's not like a classical game, but still very interesting from game theory point of view. That is the whole
What
thing.
was the name you said? The oldest game.
Oldest game.
Okay.
I'm not sure if it is still there. It used to be there on Netflix. I saw it many years ago, but it was a very cool example of game theory. I mean, they've not explained it as game theory, but now that you have studied game theory, you can start to think of it in those terms. Okay, so I'm afraid we have reached the end of our time, and I think I have covered most of the points which you guys wanted to cover. I have not covered the second bid auction, which you wanted me to cover also, but I think in the other TE class that guy has covered it. I just looked at the slides and I think he has covered the second bid auction. So if you like, you can look at his slides. I didn't see his explanation, but if you still feel like you're uncomfortable with second bid auction, you can post it in the group discussion forum. I check it pretty regularly. So I will post some notes on it in the same shared folder where I'm posting these things. We just kind of ran out of time.
Thank you.
Okay?
Yeah, thanks.
But this approach is basically what I wanted you to be clear on when you're given variables and multiple values and things like that. I will share all these slides. Please look at the group discussion forum. That is where I will be posting anything which I have not been able to share anywhere else. Okay, I will share all the links and everything and the video. And please join again. Let's hope I see just as many people in the next
Thank
class.
you.
We have classes on
Thanks.
Tuesday. All right, everyone. Thank you. Okay, have a nice day. Bye.